How did certain ancient cultures count large numbers?
It is not surprising that one of the earliest ways to count was the most obvious, using the hands. And because these counting machines were based on 5 digits on each hand. Most cultures invented numbering systems using base 10. Today, we call these base numbers or base of a number system the numbers that determine place values. For more information on base numbers, see Math Basics. However, not every group chose 10. Some cultures chose the number 12, or base 12. The Mayans, Aztecs, Basques, and Celts chose base 20, adding the 10 digits of the feet. Still others, such as the Sumerians and Babylonians, used base 60 for reasons not yet well understood. The numbering systems based on 10, or 12, 20, or 60 started when people needed to represent large numbers using the smallest set of symbols. In order to do this, one particular set would be given a special role. A regular sequence of numbers would then be related to the chosen set. One can think of this as steps to various floors of a building in which the steps are the various numbers. The steps to the first floor are part of the first order units. The steps to the second floor are the second order units, and so on. In today's most common units, base 10. The first order units are the numbers 1 through 9, the second order units are 10 through 19, and so on.
How is math used to calculate the pressure behind a dam?
There are many engineering considerations and calculations needed when building a dam. The most important being the water pressure behind the structure. Engineers know that as the elevation of water behind a dam increases, the height and density of the water causes higher pressures at the bottom of the dam. Thinking in mathematical terms, the horizontal force acting on the dam is the integral of the water pressure over the area of the dam that is in contact with the water. The force exerted by the water pushes horizontally on the dam face, and this is resisted by the force of static friction between the dam and the bedrock foundation on which it rests. The water also tries to rotate the dam about a line running along the base of the dam. The torque resulting from the weight of the dam acts in the opposite sense. For example, take the water pressure on a dam, such as the Hoover Dam on the Colorado River between Arizona and Nevada. Before building that dam, engineers needed to know the pressure not only along the entire structure, but also and especially at its base. In general, the pressure exerted by water equals the density times the depth, in which the density of water is 62.4 pounds per cubic foot. For Hoover Dam, this gives a pressure of 37,440 pounds per square foot, or 18.72 tons per square foot. The pressure calculated at half the height of the dam is 9.36 tons per square foot. This is why the base width of the dam is 1,660 feet, 201.2 meters. It is thicker to compensate for the increase in pressure at the bottom of the dam, while the width of the crest of the dam is only 45 feet, 13.7 meters.
What is an exponential function?
Along with exponents come exponential functions, or the relationship between values of a variable and the numbers formed by raising some positive number to the power of those values. In functional notation, an exponential function is written f x equals x, in which a is a positive number. For example, the function f x equals 2x is an exponential function. In logarithmic terms, an exponential function is most commonly written as exp or x, in which e is called the base of the natural logarithm. These types of functions are usually shown on a graph. For more information about graphs, see geometry and trigonometry. As a function of the real variable x, the resulting graph of x is always positive, or above the x-axis and increasing from left to right. Although the line of such a function never touches the x-axis, it gets very close to it.
Are advances in technology fundamental to our understanding of materials?
Yes, advances in technology are truly fundamental to our understanding of materials, and vice versa. For example, transistors and superconductors were developed by understanding the mathematics of the materials that make up these objects. Math and materials science together have also advanced technology used in infrastructure, such as highways and overpasses, aerospace, such as satellites and shuttles, and microelectronics, such as those found in automobiles. Today, the need to describe material behavior resulting from physical interactions is forcing scientists to develop new mathematics. In fact, materials science has evolved to the point in which researchers from physics, engineering, and applied mathematics are working together on common problems.
What is Ohm's law?
Ohm's law is important to the field of electrical studies. It states that direct current flowing in a conductor is directly proportional to the potential difference between its ends. First summarized by German physicist George Simon Ohm, 1789 to 1854, it is usually seen in formula form as V equals IR, or I equals V/R, in which V is the potential difference, voltage. I is the current, also written in some texts as I, and R is the resistance of the conductor. This can also be written in terms of electric quantities. Voltage equals current x resistance, and with units of measure, volts equals amps x ohms.
In what ways does mathematics apply to music?
There are many ways in which mathematics applies to music, from harmonics to the concept of octaves and scales. There is a most interesting connection in that both music and mathematics are experienced as pure objects of the brain, and both have meaning outside of the brain only through artificial connections. For example, there is a mathematical reason why certain note combinations sound harmonious to most people. One good example is a violin string. When it is plucked, the string vibrates back and forth, creating mechanical energy that travels through the air as wave patterns. The number of times the waves reach a person's ear is called the frequency, which is measured in hertz, or cycles per second. If more waves are heard within a certain time period, the note's pitch sounds higher. Chords sound harmonious to us because of waves and ratios. For example, take the C major chord, in which the note middle C is 261.6 Hz. The note E is 329.6 Hz, and the note G is 392.0 Hz. The ratio of E to C is about 5/4, or every fifth frequency wave of E matches with every fourth wave of C. The ratio of G to E is also about 5/4, and the ratio of G to C is about 3/2. Because the notes' frequencies match with the other notes' frequencies, they all sound harmonious to a person's ear. It is interesting to note that none of the ratios for the familiar Western-style scale are truly exact, but rather are approximations. This is because when this scale was put together, the creators wanted to make the notes go up in equal intervals and the ratios to be in tune. The only way to do this was to compromise and use inexact ratios.
What are some examples of logarithm use?
Logarithms are used in many areas of science and engineering, especially in those areas in which quantities vary over a large range. For example, the decibel scale for the loudness of sound and the astronomical scale of stellar brightness are both logarithmic scales. Log A equals 1, because A equals A. For example, in the equation 31 equals 3, the base is 3 and the exponent is 1, the result is 3, with the corresponding logarithmic equation being log 3 equals 1. X 4 log A equals X, because A equals A. For example, 4 equals 3, with the base as 3. The logarithmic equation becomes log 3 equals 4.
Is there such a thing as a perfect number?
Yes, there is such a thing as a perfect number, but it is not what we think of as true perfection. To mathematicians, perfect numbers are somewhat rare. They are defined as a natural number, or positive integer, in which the sum of its positive divisors, or the bottom number in a fraction that divides the number to equal another whole number, and includes 1 but not the number itself, is the number itself. For example, 6 is considered a perfect number because its divisors are 1, 2, and 3, or 1 plus 2 plus 3 equals 6. The next perfect numbers are 28, 1 plus 2 plus 4 plus 7 plus 14. 496, 8128, 33,550,336, 8,589,869,056, 137,438,691,328, 2,305,843,008,139,952,128, and so on. Larger and larger perfect numbers are still being discovered, especially with the help of today's faster and more memory-packed computers.
How do surveyors make measurements?
Most of a surveyor's measurements are gathered with a theodolite, an instrument that acts as a telescope, ruler, and protractor. The theodolite is set up over a known spot, such as a previously surveyed corner of a lot. Its telescope then sights a specific spot, such as another corner of a lot, and the distance is measured. Most modern theodolites use lasers to measure distance, supplemented by angular measurements in both the horizontal and vertical planes. The surveyor then uses trigonometry to analyze the data, converting it to a more usable form, usually in x, y, and z coordinates. For example, depending on the desired outcome, the vertical angle and slope distances can be converted from polar measurements to show differences in elevations and horizontal distances. The horizontal distances and angles can also be converted from polar measurements to rectangular coordinates. For more about coordinates, see geometry and trigonometry.
How does one sample a population?
Sampling is the term used when one obtains a sample of a population. The number of members in the sample is called the sample size. As with most mathematical concepts, there are several types of sampling. Random sampling is a technique involving a group of subjects, the sample, from a larger group, population. It is a method that reduces the likelihood of bias. In random sampling, each individual is chosen by chance, with each member of the population having a known, but often unequal, chance of being included in the sample. Simple random sampling also involves a group of subjects, the sample, from a larger group, population, but in this case, each individual is chosen entirely by chance. with each member of the population having an equal chance of being included in the sample. In fact, each member of the population has an equal chance of being chosen at any stage of the sampling process. Independent sampling comprises samples collected from the same or different populations that have no effect on one another. In other words, there is no correlation between the samples. Stratified sampling includes random samples from various subgroups, also called subpopulation or stratum of the population, chosen to be representative of the whole population. It is often thought of as a better technique than simple random sampling. For example, if a sheep farmer wanted to determine the average weight amount of wool gathered from 3 types of sheep on his farm, he could divide his flock into the 3 subgroups and take samples from those groups. In cluster sampling, the entire population is divided into clusters, groups, then a random sampling is taken of the clusters. This technique is used when a complete list of the population's members can't be studied, but a list of population clusters can be gathered.
What is mathematical medicine?
Mathematical medicine uses math to understand certain medical problems. For example, some medical researchers are using noises and sounds from a patient's lungs as a diagnostic tool. Based on the quality of the sound measured by ear or mathematical analysis of a frequency spectrum, it may prove to be a non-invasive way of detecting lung disease. Other examples are the mathematical modeling of how drugs are delivered through the body to target diseases and the mathematical modeling of the progression of age-related macular degeneration. Overall, mathematical modeling and simulation techniques are the most important part of mathematical medicine, and will likely be used in the future to help solve problems with the human body.
What are the least common multiple and denominator?
The smallest common multiple, whole number, of 2 or more whole numbers is called the lowest, or least, common multiple, LCM. For example, for the numbers 3 and 8, the multiples of 8 are 8, 16, 24, 32, and so on. The multiples of 3 are 3, 6, 9, 12, 15, 18, 21, 24, 27, and so on. Therefore, the LCM of 3 and 8 is 24. The least common denominator, LCD, is mainly used to carry out the addition or subtraction of fractions. In order to do these operations, the fractions need to have the same denominator. For more information about fractions, see below. The easiest way to work on such calculations is to determine the lowest number possible for the denominator, a number called the least common denominator, LCD, which is actually the common factor by which 2 numbers are divisible. For example, To add 1/6 and 1/8, we have to find the least common multiple of the denominators. In this case, the number is 24, multiply 1/6 x 4/4 and 1/8 x 3/3, to change each addend to some number of 24 ths. Or 1/6 x 4/4 equals 4/24, and 1/8 x 3/3 equals 3/24. Thus, 1/6 plus 1/8 equals 4/24 plus 3/24 equals 4 plus 3/24 equals 7/24.
Why is Laplace transform important in engineering?
Laplace transform is a way to solve linear differential equations and translate them into simple algebraic problems that are easier to solve. It was developed by French mathematician and theoretician Marquis-Pierre Simon de Laplace, 17491827. Although it carries his name, the Laplace transform seems to have been first used by Denis Poisson, 1781–1840, in 1815. Today, it is used extensively in electrical engineering problems.
What is the Fibonacci sequence?
Italian mathematician Leonardo of Pisa, c. 1170 c. 1250, also known as Fibonacci, or son of Bonaccii, although some historians say there is no evidence that he or his contemporaries ever used the name. May be known for helping to introduce Hindu-Arabic numerals to Europe, CP 70, but he also is famous for the sequence of numbers he discovered. This sequence initially pursued as an exercise to determine how fast a pair of rabbits can reproduce per year is formed by adding the two preceding numbers to find the next number, starting with a pair of ones. Thus, the Fibonacci numbers in the sequence are 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233, 377, and so on. Or 1 plus 1 equals 2, 2 plus 1 equals 3, 3 plus 2 equals 5, 5 plus 3 equals 8, 8 plus 5 equals 13, 13 plus 8 equals 21, 21 plus 13 equals 34, 34 plus 21 equals 55, 55 plus 34 equals 89, 89 plus 55 equals 144, 144 plus 89 equals 233, 233 plus 144 equals 377, and so on.
What is a Vedic square?
Historically, in order for Islamic artisans to create a variety of geometric patterns, a Vedic square was often used. The Vedic is an ancient religion associated with India. For more information, see below. These squares generate patterns by the selection of number sequences and angles. Each square is made by taking a multiplication table and reducing all the numbers to single digits. For example, if a number in the table was 81, it would be reduced by adding 8 plus 1, or 9. Then, to get a design, for example, a certain line of numbers would be chosen, such as connecting all the number 5s. And by using a fixed angle of rotation with the lines, various designs were drawn. These number patterns are distinctively Islamic and helped create many of the famous traditional Islamic geometric designs seen today.
How is a decision problem connected to algorithms?
A decision problem is also known as an Entscheidungsproblem, which stems from the German. Decision problems bring up the question of whether an algorithm represents a specific mathematical assertion or not, as well as whether it has or does not have a proof.
How are points determined in a real estate transaction?
Hen buying a home through a real estate group or bank. Points may be paid by the borrower at the time a loan is made. This is usually to get a lower interest rate, because the lender often offers certain rate/point combinations that may help the homeowner save money. Actually, points usually refer to the commission charged by the mortgage broker or the loan fee charged by the lender when the loan is made. Points can be also negative, in which case they are called rebates from the lender to the borrower and are often used by borrowers to defray other settlement costs. In general, each point is 1% of the loan amount. For instance, 3 points would be equal to 3% of the total loan amount. There is no set number of points offered by a lender, as it is not controlled by any laws. For example, on a $100,000 loan, 1 point is equal to $1,000, 10 points is equal to $10. 000. A homeowner looking for a loan should try to find a mortgage broker or lender that charges fewer points. Some financial institutions might even be willing to negotiate for lower points. But beware of lenders offering no or 0 points, because they usually charge much higher interest rates than those offering loans with points. Although it is a matter of mathematics and a person's budget, there are some very general guidelines when choosing a mortgage. Low-rate, high-point loans are usually used by borrowers who can meet the down payment cash requirement and either want to stay in a house a long time or want to reduce their monthly mortgage payments. High-rate, low-point combinations are for borrowers who don't expect to be in their houses very long, or who are short on cash.
What are the cube and the cube root?
Much like a square, a cube is when you multiply a real or complex number by twice itself, making a total of 3 numbers. Mathematicians express the cube of a number using the superscript 3, or For example, 23, or 2x2x2. Unlike a square of a number, the cube of a number will not always be positive. Such as minus 3x minus 3x minus 3, which equals minus 9. A cube root is a number that when multiplied by itself 2 more times has the product of s, in which t3 equals s. For example, the cube root of 125, s, is 5, t, or written as v31-25 equals 5, the cube root of minus 125 is minus 5.
How are algorithms connected to computers?
Algorithms are essentially the way computers process information. In particular, a computer program is actually an algorithm that tells the computer what particular steps to perform and in what order so a specific task is carried out. This can include anything from working out a company's payroll to determining the grades of students in a certain class. For more about algorithms, see Foundations of Mathematics.
Are there double and triple integrals?
Yes, there are double and triple integrals and even multiple integrals in equations, jj, and so on. For example, the integration of a function of 3 variables, w equals f, x, y, z, over a 3-dimensional region R in xyz space, 3-dimensional space, is called a triple integral.
Why was Alan Turing so important to the development of computers?
Living in his native England during World War II, Alan Turing was instrumental in deciphering German messages encrypted by the Enigma cipher machine. Shortly after the war, he designed computers first for the British government. 1945 to 1948, then for the University of Manchester, 1948 to 1954. He also wrote several works on the field of artificial intelligence. A study in its infancy at the time, and developed the theory of the Turing test, in which a computer is tested to see if it is capable of human-like thought. Tragically, Turing, who is often considered the founder of computer science, committed suicide in 1954.
Can Newton's 3 laws be expressed mathematically?
Yes, Newton's 3 laws are all based on mathematical formulas. But the equations would be too complex for this text. They are defined, some with applicable mathematical notation, as follows: Newton's first law. Law of inertia states that without any forces acting on an object, it will maintain a constant velocity. In other words, an object will stay still or keep moving in a straight line until something pushes it to change its speed or direction. The one force that stops almost everything from standing completely still or moving in a straight line is gravity. This is easily seen when you throw a baseball in the air. The ball does not move in one continuous, straight direction because the Earth's gravity pulls it downward toward the surface. Newton's second law, law of constant acceleration, states that if a force acts on an object, the object accelerates in the direction of the force. The force creates an acceleration proportional to the force, and inversely proportional to the mass. This is written in the following notation: F equals ma, in which F is the force, m is the mass, and a is the acceleration. Newton actually expressed this in terms of the calculus, a form of mathematics he created to explain these physical laws. For more about the calculus and Newton, see History of Mathematics and Mathematical Analysis. Newton's third law, or law of conservation of momentum, states that forces on an object are always mutual. To put it another way, if a force is exerted on an object, the object reacts with an equal and opposite force on the phenomenon that initially exerted the force. Simply stated, objects exert equal but opposite forces on each other. This is often phrased, for every action, there is an equal and opposite reaction. The mathematical equations for these forces are complex and beyond the scope of this text.
How is mathematics used in physics to describe motion?
Everything in the universe is in motion, from the rotating Earth to subatomic particles. Motion in physics is described mainly through mathematics, including speed, velocity, acceleration. Momentum, force, something that changes the state of rest or motion of an object, torque. When a force causes rotation or twisting around a pivot point, and inertia. A body at rest remains at rest, and a body in motion remains in motion, until acted upon by an outside force. Unlike what most people think, speed and velocity are not the same. Speed is the rate at which something moves, velocity is speed in a certain direction. Speed is also called a scalar quantity, described by the following formula: speed equals distance/time. For example, if you drive 200 miles in 2 hours, and your speed is constant, your average speed is 200/2, or 100 miles per hour. On the other hand, velocity is known as a vector quantity. For more about vectors, see mathematical analysis. That gives velocity both speed and direction, and that leads directly to acceleration. When an object's velocity changes, we say that it accelerates. Acceleration, also a vector like velocity, is represented as the change in velocity divided by the time it takes for the change to occur.
What is a proof?
A proof is simply the process of showing a theorem to be correct. Although the process itself might not be simple. These mathematical arguments are often quite rigorous. And they are used to demonstrate the truth of a given proposition. The result of the proved statement is a theorem. Interestingly enough, there are several computer systems now being developed to automate proofs. But some mathematicians, mostly purists, do not believe these computer-assisted proofs are valid. They believe that only humans can understand the nuances and have the intuition needed to develop a theorem's proof. One good example is called the four-color theorem. Its proof relies on meticulous computer testing of many separate cases, all of which can't be verified by hand.
What are dice?
Dice are small cubes usually used in games of chance. Each dice is the plural, has 6 sides numbered with dots from 1 to 6. The dots are placed on the cube so that the sum of dots on opposite sides equals 7. The total number of dots on each die equals 21. They are mostly associated with certain types of games. With the simplest involving a player, or many players, who throw, or toss or roll, the dice for the highest sum. Dice have been around for more than 3,000 years, with evidence found in ancient Egyptian tombs, Chinese burial chambers, and the ruins of Babylon. The Greeks and Romans were avid users of dice and associated games. And they have been popular from the Middle Ages on. Dice have been made from many materials, including ivory, bone, wood, metal, and eventually plastic. Not all dice are square. The cube, or hexahedron, belongs to the group of 5 Platonic solids, or solids formed by regular polygons. Thus, other Platonic solids have also been made into dice, including shapes, polyhedra, such as tetrahedrons, octahedrons, and dodecahedrons, which are used for certain types of games. For more information about Platonic solids and polyhedra, see geometry and trigonometry.
What are the Lotka-Volterra interspecific competition logistic equations?
The Lotka-Volterra interspecific competition logistic equations are concerned with the predator-prey relationships between species in the environment, and are based on differential equations. For more on differential equations, see mathematical analysis. Such predator-prey theories were developed independently by then Austrian, now the Ukraine, chemist, demographer, ecologist, and mathematician Alfred James Lotka. 1880 to 1949, and Italian mathematician Vito Volterra, 1860 to 1940, in 1925. They refer to interspecific competition, or the competition between two or more species for some limiting resource, such as food, nutrients, space, mates, nesting sites, or anything in which the demand is greater than the supply. Most people think about the AQI in terms of being outdoors, and most weather broadcasts include air quality listings, especially in larger cities. When the readings are high, people are warned not to participate in strenuous activities like sports or hard work outside. People with asthma or other lung problems are urged to stay inside.
Who built the first known adding machine?
No one knows who built the first adding machine. Although many historians believe it was German mathematician Wilhelm Schickard. 1592 to 1635, who first invented a mechanical calculator in 1623 based on Napier's bones, see above. Schickard and his family perished from the bubonic plague. It was not until the mid-20th century that his notes and letters were discovered. They showed diagrams of how to construct his machine. Schickard apparently built two prototypes. One was destroyed in a fire and the other one's location is unknown, if it survived at all. His device, which he called the calculating clock, was able to add and subtract up to 6-digit numbers using a mechanism of gears and wheels. But not all historians credit Schickard. Some believe that there was an even earlier attempt at mechanical computing by Leonardo da Vinci, who also apparently designed an adding machine. Some of his notes were found in the National Museum of Spain in 1967 and describe a machine bearing a certain resemblance to Pascal's machine, see below.
What are some examples in which probability is used?
There are thousands of examples in which probability is used. Some are familiar, and some originate from the seamier side of life. For example, everyone has played at coin tossing at one time or another. Although there is no such thing as an idealized coin as circular one of 0 thickness, most coin tosses use the coins available, with either side face up. Heads or tails, also phrased heads up/down or tails up/down. Thus, one can think of a coin as a two-sided die in lieu of the six-sided cubes we are all used to in a game of dice. If a coin is tossed with a good amount of spin, we can denote the two possible results as H for heads and T for tails. If we repeat the tosses n number of times, we obtain n, H, heads and n, T, tails. Thus, the fraction of n, H, /n and n, T, /n can be thought of as the chance probability, to get a head or tail, respectively, P, H, and P, T, are the most common notations that represent the probability to get heads and tails, respectively. If we toss the coin many times, the result should be close to 0.5. Of course. This means that if we bet on the chances of heads and tails, we will not be much of a winner if we Play too many games and we will have to have really good luck to win if we play fewer games. Chuck-a-Luck is a gambling game that has been played at many carnivals over the years. It involves a player who may bet on any one of the numbers 1 through 6. Based on 3 dice placed in a cage. If a selected number appears, the gambler gets paid even money, if one of the numbers comes up twice. The gambler gets paid 2 to 1, and if the desired number comes up 3 times. The gambler gets paid 3 to 1. But if the player worked it out, he or she would find that the game's expected odds are worse than for almost any other table game of chance. The game is sometimes used as a fundraiser for charity. But the odds of coming away with more money than originally put in are quite small. And they are even worse if someone has loaded the dice. Probability can also be associated with the violent game of chance called Russian roulette. In this bizarre sport, one or more of the 6 chambers of a revolver are filled with bullets. The magazine is rotated at random, and the gun is fired at the player's head. The risk taker bets on whether or not the chamber that rotates into place will be loaded. If it is, he loses not only his bet but also his life. Not to be outdone, there are people who have come up with a modified version of Russian roulette. In this case, the gun is loaded with a single bullet and 2 duelists alternately spin the chamber. Each duelist fires at the other until one is killed. The probability of the first duelist being killed is 6/11.
What is the mathematical distinction between weight and mass?
There is a definite difference between weight and mass, which is easily represented in the formula W equals mg, in which W is weight, or the gravitational pull on an object. M is mass, or the quantity of matter in an object, and g is the gravitational pull. For example, if you wanted to lose weight, you could move further from the Earth or live on the Moon. In both cases, the gravitational pull would be less. But remember, no matter where you travel in the universe, you will always have the same mass unless you diet.
What was the Babylonian numbering system?
The Babylonians were one of the first to use a positional system within their numbering system. The value of a sign depends on the position it occupies in a string of signs. Neither the Sumerians nor the Akkadians used this system. The Babylonians also divided the day into 24 hours, an hour into 60 minutes, and a minute into 60 seconds, a way of telling time that has existed for the past 4,000 years. For example, the way we now write hours, minutes, and seconds is as follows: 6h, 20, 15. The way the Babylonians would have written this same expression, as sexagesimal fractions, was 6 and 20/60 15/3600.
How does one determine the distance and amount of time a trip will take?
There are several ways to determine the distance and amount of time a trip will take. For example, if the traveler knows that his or her car travels 20 miles for every gallon of gas in the tank, he or she could represent the total number of miles it is possible to drive based on how much gas is put into the tank. This can be expressed as 20G, in which G stands for the number of gallons in the tank. For example, if someone bought 10 gallons of gas to reach a destination, 10 gallons x 20 miles/gallon, the traveler can go about 200 miles. The gallons in the top and bottom of the equation cancel each other out, leaving miles. Another example involves cars and mileage. If the traveler drives down a highway at a steady rate of 65 miles per hour, the driver can determine how long it will take to get to a destination, especially if he or she knows how many miles it is to that destination. The equation is mileage divided by 65 miles per hour, m/65. For example, if the traveler is going 650 miles, the 650 miles / 65 miles per hour equals 10 hours. The miles in the top and bottom of the equation cancel each other out, leaving hours.
How are angles measured?
Angles are measured in two major ways, degrees and radians. Similar to degrees on a temperature scale. Degrees in mathematics, especially when discussing angles, are usually denoted by the symbol degree. They are divided into 60 arc minutes, and arc minutes are divided into 60 arc seconds. The multiples of 60 are thought to be connected to the Babylonian sexagesimal number system. One based on the number 60, in which the year was composed of 360 days, or 12 months at 30 days each. If the vertex of an angle and one side are fixed and the other side is rotated about the vertex, it sweeps out a circle of 360 degrees with each complete rotation. Said another way, a full rotation is 360 degrees. Radians, denoted as rad, are real numbers represented as an angle. They are the central angle of a circle determined by two radii and an arc joining them. In degrees, a radian is about 57.29578 degrees or 180/pi degrees, because a semicircle contains pi radians. For example, pi/6 is equal to a 30-degree angle, because a straight angle is pi radians. Or 180 degrees, if you divide 180 by 6, or pi/6, it is equal to 30 degrees. Radians are most often used in probability and statistics, or calculus, especially to obtain the derivative of trigonometric functions.
How do various disciplines use applied mathematics?
Depending on the discipline, researchers use applied mathematics in various ways. For example, some disciplines rely heavily on pure mathematics. Numerical analysis, a form of applied mathematics, is a field that uses pure mathematics to decipher partial differential equations and variational methods. For more information about numerical analysis, see below. For partial differential equations, see mathematical analysis. There are also areas of applied mathematics that overlap other fields of study. For example, there are mathematicians who use applied mathematics to study the structure of matter, especially the behavior of subatomic particles, a field that also overlaps the same types of studies done by subatomic physicists.
What is the air quality index?
Mathematics plays an important part in the Air Quality Index, AQI, a scale developed by the U.S. government to measure how much pollution is in the air. The AQI measures 5 specific pollutants: ozone, particulate matter, carbon monoxide, sulfur dioxide, and nitrogen dioxide. The levels range from 0, good air quality, to 500, hazardous air quality. The higher the index, the higher the level of pollutants and the greater the likelihood of detrimental health effects.
How are three-dimensional Cartesian coordinates determined?
The three-dimensional coordinates are those that describe a solid or three-dimensional object with 3 axes or 3 planes, the usual 2 axes, as in the two-dimensional system, and an additional line. The coordinates are usually written in terms of x, y, and z, and are often called ordered triples or just triples.
What are some examples of mathematical models used by chemical engineers?
There are numerous examples of how mathematical models are used by chemical engineers, too many to mention them all here. One good example is modeling crystal growth. Liquids from water to molten metals become crystalline solids as they are cooled. Engineers can mathematically design software that helps in the manufacture of superior crystalline growth, especially for electronics and other industries. These improved crystal forms advance the quality of electronic hardware, including computers, and help engineers design better alloys for a wide range of applications.
What was the gambler's ruin?
In the problem, if a player begins with $10 and intends to play the game repeatedly until he either goes broke or increases his holdings to $20. The question asked is, what is his probability of going broke? The answer involves quite a bit of probability computation. For more information about the gambler's ruin, see recreational math.
Are random numbers generated by a computer truly random?
For most general purposes, random numbers generated by a computer can be considered random. But in reality, because a computer follows a set of rules in any program, the numbers generated are not truly random. In order for a sequence or specific numbers to be truly random, they must not follow any sort of rules. That's something to think about the next time you purchase a computer-generated random numbers lottery ticket.
What is the Gregorian calendar?
By 1582 the discrepancies in the Julian calendar were not interfering with timekeeping, but they were beginning to infringe on dates of the Church's ecclesiastical holidays. The powerful Catholic Church was not amused. Pope Gregory XIII, on the advice of several of his astronomers, decided to reposition days, striking out the excess 10 days that had accumulated on the then present-day calendar. Thus, October 4, 1582, was followed by October 15, 1582, to fix the extra days problem. The Pope made sure that the last year of each century would be a leap year, but only when it is exactly divisible by 400. That means that 3 leap years are suppressed every 4 centuries. For example, 1900 was not a leap year, but 2000 was a leap year. Today, the Gregorian calendar rules state that every year divisible by 4 is a leap year, except for years that are both divisible by 100 and not divisible by 400. Some countries eliminated the 10 extra days, starting fresh with the Gregorian calendar. But not everyone agreed with the new calendar, especially those who distrusted and disliked the Catholic Church. Eventually, by 1700 those who had not changed their calendars had collected too many extra days. In 1752, the English Parliament decreed that 11 days would be omitted from the month of September. England and its American colonies began to follow the Gregorian calendar, with most other countries following close behind. It is now the standard calendar used around the world.
What did the Chinese add to the study of mathematics?
Despite the attention the Greeks have received concerning the development of mathematics, the Chinese were by no means uninterested in it. About the year 200 BCE, the Chinese developed place value notation, and 100 years later they began to use negative numbers.
What is the fundamental theorem of the calculus?
The fundamental theorem of the calculus is the connection, or, more accurately, the bridge, between the integral and the derivative, in other words. It is another way of finding the area under a curve, see above, by evaluating the integral. In particular, if f, x, is a function whose derivative is f, x, then the area under the graph of y equals f, x, between the points a and b is equal to f, b, f, a.
What is chaos theory?
Chaos theory is one of the newest ideas in mathematics. Developed in the last half of the 20th century, it affects not only math, but also physics, geology, biology, meteorology, and many other fields. Modern ideas about chaos began when theorists in various scientific disciplines started to question the linear analysis used in classical applied mathematics, most of which presumes an orderly periodicity that rarely occurs in nature. In the search to discover regularities, the idea of disorder had been ignored. To overcome this problem, chaos theorists developed deterministic, nonlinear dynamic models that explain irregular, unpredictable behavior. By 1961, American meteorologist Edward Norton Lawrence, 1917, noticed that small variations in the initial values of variables in his primitive computer weather model resulted in major divergent weather patterns. His discovery of a simple mathematical system with chaotic behavior led to the new mathematics of chaos theory. The use of chaos theory has enabled scientists and mathematicians to reveal the structure in aperiodic, unpredictable dynamic systems. For example, it has been used to examine crystal growth, the expansion of pollution plumes in water and in the air, and even to determine the formation of storm clouds. One of the reasons chaos theory has come to the forefront of science and mathematics is because of advancements in computers. High-end computers allow for a plethora of variables to enter into the complex chaos equations.
What are complex numbers?
Complex numbers have two parts, a real part, any real number, and an imaginary part, any number with an I in it. The standard complex number format is a and by, or a real number plus an imaginary number. It is also often seen as x and e because while real numbers are viewed on a line, complex numbers are viewed graphically on an argand, or polar, coordinate system. The imaginary numbers make up the vertical, or y, axis as e, while the horizontal, or x, axis is occupied by real numbers. For more information about coordinate systems, see geometry and trigonometry.
What are some special properties of zero?
There are many special properties of 0. For instance, you cannot divide by 0, or have 0 as the denominator bottom number of a fraction. This is because, simply put, something cannot be divided by nothing. Thus, if some equation has a unit, usually a number, divided by 0, the answer is considered to be undefined. But it is possible to have 0 in the numerator, top number, of a fraction. As long as it does not have 0 in the denominator, called a legal fraction, it will always be equal to 0. Other special properties of 0 include, 0 is considered an even number. Any number ending in 0 is considered an even number. When 0 is added to a number, the sum is the original number. And when 0 is subtracted from a number, the difference is the original number. Square of the length of the radius, or as it is often phrased, pi r squared.
What is a slide rule?
The slide rule is a ruler-like device with logarithmic scales that allows the user to do mathematical calculations. It is portable, with the most common slide rules using 3 interlocking calibrated strips. The central strip can be moved back and forth relative to the other two. Calculations are performed by aligning marks on the central strip with marks on the fixed strips, then reading marks on the strips. There is also a see-through sliding cursor with a hairline mark perpendicular to the scales, allowing the user to line up numbers on all the scales. Sadly for mathematical traditionalists, the use of the slide rule was eventually overtaken by the pocket calculator by the mid-1970s. But in other ways, this development was welcome. The slide rule had two major drawbacks, especially for calculations in mathematics, engineering, and the sciences. It was not easy to add with the device and it was only accurate to 3 digits.
How can vectors be represented in various dimensional space?
Vectors can be found in 2-, 3-, or multi-dimensional space. Two-dimensional vectors are seen visually on a graph as a line with an arrow connecting 2 points. A two-dimensional vector is defined by length and direction measured by the angles that the arrow makes with the x and y coordinate system axes. A vector in such a coordinate system is written as two components, x, y. Vectors in a three-dimensional space are represented with 3 numbers, one along each coordinate axis. These are the coordinates of the arrow point, usually as x, y, z, if the arrow starts at the origin. A more complex vector is one with multiple components, in which several different numbers in ordered n-tuples represent a vector. For example, 4, 1, -2, 0, is an ordered 4-tuple representing a vector in 4 dimensions.
What are permutations, combinations, and repeatables?
In order to perform certain probability problems, specific counting techniques need to be used, including determining the number of permutations, combinations, or repeatables. The following explains each term. The examples are based on a set of 5 cats on a shelf A, B, C, D, and E, for convenience. Note, the cats can be arranged in 120 ways, expressed as 5x4 x3 x2 x1 equals 5. 5 factorial equals 120.
How does one determine the distance and amount of time a trip will take?
There are several ways to determine the distance and amount of time a trip will take. For example, if the traveler knows that his or her car travels 20 miles for every gallon of gas in the tank, he or she could represent the total number of miles it is possible to drive based on how much gas is put into the tank. This can be expressed as 20g, in which g stands for the number of gallons in the tank. For example, if someone bought 10 gallons of gas to reach a destination, 10 gallons x 20 miles/gallon, the traveler can go about 200 miles. The gallons in the top and bottom of the equation cancel each other out, leaving miles. Another example involves cars and mileage. If the traveler drives down a highway at a steady rate of 65 miles per hour, the driver can determine how long it will take to get to a destination, especially if he or she knows how many miles it is to that destination. The equation is mileage divided by 65 miles per hour, m/65. For example, if the traveler is going 650 miles, the 650 miles / 65 miles per hour equals 10 hours. The miles in the top and bottom of the equation cancel each other out, leaving hours.